Hi, let's review for your Investigation 3 quiz. So for your Investigation 3, you need to be able to explain why the atomic model changed over time, be able to identify the atomic number of protons, neutrons, electrons, the mass number, and the average atomic mass for any atom. And that average atomic mass would be what's the average of the element that that atom belongs to. You need to be able to recognize isotopes, relative abundance, calculate average atomic mass, and write isotopic symbols, and know the parts of the atom. These two are starred because we went over them in a previous video, so you can rewatch that. I will address isotopic symbols and relative abundance in this video. Okay, and there's more. We'll rate complete and abbreviated electron configurations. So first, let's talk about how and why the atomic model changed over time. So the general answer for that is that as we know more and more about something, we change our idea about it. So initially, scientists didn't know very much at all about the atom, so the model is pretty vague. And as they learned what parts were there, the model had to reflect the parts that they knew existed. So initially, scientists just noticed that no matter how much of an element, so for example, no matter how much gold you had, that gold behaved the same. So it would be just as shiny and the same density and the same color and the same malleability. So it had the same properties whether you had twice as much gold or half the amount of gold. You know, it was just like it was made of these identical pieces. And with a little more detail, Dalton observed that if he mixed different elements together, they would combine in these whole number ratios. So he figured out that all the matter around us must be made of these different building blocks, and the building blocks combine in a 1-to-1 ratio, a 1-to-2 ratio, a 2-to-3, a 3-to-4, all these different whole number ratios. And so the first model was the billiard ball model. Billiard ball. So they just thought that the atom was like a little sphere, and it was the same throughout. There weren't any positive particles, no negative particles, no neutral particles. It was just a solid particle that had no charge. Then J.J. Thompson succeeded in removing negatively charged particles from a sample of atoms. So they said, okay, well, our old model didn't have negatively charged particles, so let's add negatively charged particles to our model. Okay, so now they called this the plum pudding model. You can think of it like a chocolate chip cookie where it's kind of the same dough throughout with little chocolate chips. So it would be the same positive type stuff throughout with these little negative particles here and here. Although I don't think there's anything negative about chocolate. So next, Rutherford recognized that if he shot alpha particles at a really thin sheet of gold, which was a thin sheet of atoms, most of those particles went straight through, but some bounced back. And this model doesn't really explain why some particles would go through and some would go back, because this model is pretty much the same throughout. So he said, well, there must be a really, really, really dense part of an atom, and we call that the nucleus. So there's this tiny dense part, and that has like all the matter. And if an alpha particle hits that one dense part, it bounces back. And he said the rest of the atom, great, is made of electrons orbiting that nucleus. It's a really good drawing here. That's special there. That's good. Okay, so that you have this one really dense part, the nucleus, and then the negative particles were somewhere in the outside. Okay, so the next, Bohr realized that some electrons were easier to remove than others. So this one didn't make sense because all these electrons spend an equal amount of time away from the nucleus and close to the nucleus. And since electrons are negative and the nucleus is positive, you would think that it'd be easier to remove electrons that are farther away. So he said, okay, well, that must mean you've got your positive nucleus in the center. And then you have some electrons that are traveling around that positive nucleus pretty close, and other electrons that are traveling around the nucleus, but they're farther away, and others still that are even farther away, and it's easier to remove. Those are all supposed to be circles, by the way. it's easier to remove those electrons that are farthest away. It's pretty hard to remove them when they're close because these are closer to the thing they're attracted to. These negative parts are farther from the positive thing they're attracted to. So next, we only talked about this to this level that Heisenberg and Schrödinger realized that the electrons weren't traveling in these perfect little circles. Instead, they predicted these regions of probability where electrons reside. And those regions are actually the subshells that we talk about. So the S subshell or the P subshell or the Ds. And also Chadwick identified that neutrons exist. So now I have to make my nucleus big because I can't show positive and negative particles on that little dot that I was drawing. So here we go. I'm going to just draw helium. So that's a positive, or actually, yeah, there's a positive. Let's give it one more positive. Now it's helium. And there. Okay. And then I'm just going to say there's this electron cloud. So the electrons are somewhere. And this is one electron that could be in any place at any time. I'm trying to draw a cloud. Okay, so this guy has 2 protons. It would only have 2 electrons, but those 2 electrons are constantly moving in different little patterns. Okay, and that is why we moved from model to model. Next, we have to be able to identify the atomic number. And the atomic number is the number of protons. You can just look on your periodic table. It's the whole number that is written above your element symbol. The number of protons, that's the same as the atomic number. The number of neutrons, you'll either be given the number of neutrons or you'll be given the mass number to figure out the number of neutrons, because protons plus neutrons equals the mass number of one atom. Because the mass number is pretty much how many protons plus neutrons an atom has, or how much one atom weighs. Number of electrons is always equal to the number of protons in an atom, and we're only talking about atoms so far. So for every one positive particle, we have one negative particle, and that's why our atoms are neutral. The positive and the negative cancel each other out. Let's see, so that mass number, we said again, that's protons plus neutrons to get the total mass of the atom, of that one atom. An average atomic mass is looking at all of the atoms in the world of that one element and taking their average mass. So for example, carbon's average atomic mass is 12.011 because most of the atoms in the world that are carbon 12. There's a whole lot of carbon 12s. There's some carbon 13s and some carbon 14s, and if you added a ton of 12s plus some 13s and some 14s, then your average would be just barely over 12. So that's why they have that average of 12.011. By the way, that's where you get your relative abundance. If you see that an atom's average atomic mass is 12.011, well, you know it's made from atoms of different mass. So you would guess a mass number above and below. So you'd guess, well, there's probably carbon 12s and probably carbon 13s. That would be a good guess for that. And seeing that this is much closer to the 12, that means there must be many more 12s than 13s to get an average of 12.011. So that's your talk on relative, or the relative abundance of isotopes. Okay, so we're going to fill this in. So the isotopic symbol, you have your number of protons and you have your mass number above, so protons plus neutrons. So that tells me my atomic number must be 20. So my number of protons is 20, and my number of electrons is 20. My mass number is 41, and since neutrons plus protons give me my mass number, well, 41 minus 20 is 21, right? Because 20 plus 21 gives me 41. That's good. And for this average atomic mass, I look on the periodic table, and I see the average atomic mass on my periodic table is 40.078 AMUs. So a good guess would be that calcium exists as calcium 40 and calcium 41, and that the calcium 40 atoms are much more common in the world. So go ahead and pause and fill in the next 2 rows. Hopefully you paused. And let's see, the thing with an atomic number of 11 is going to be sodium. and that means it has 11 protons, 11 electrons. If it has 12 neutrons and 11 protons, that's a total of 23. So that 23 is the mass number, goes on our isotopic symbol. And the average atomic mass for sodium on my periodic table is 22.99. So a good guess for the isotopes that exist in the world for sodium are sodium-22 and sodium-23, with 23 being much more common. And let's see, if this thing has 38 electrons, it has 38 protons and an average, or the atomic number of 38 as well. So 38 goes here, and my mass number is 88. And I look at my periodic table and see that strontium, Sr, has atomic number 38. So let's see, my neutrons must be 50, because 38 plus 50 is 88. And the average atomic mass of strontium is 87.62. It's a weird 7, but 87.62. So a good guess for this guy would be that strontium exists as 87 and 88, with 88 being more common, because the average is closer to that. Okay, the last thing to cover. When we write our electron configurations, the complete, you just write describe all the electrons that are there. So we talked about this being the S, the P, the D, and the F are down here. We numbered our periodic table, so we knew that this was the 1s was up here where hydrogen and helium are, 2s, 2s, 3s, 4s. D's start at 3. That's the 2p, the 3p. So your periodic table should already be numbered. So let's see, if I've got potassium's right here, and on my periodic table it says there's 19 electrons, so I should have 19 total that I described. So I go start here, hydrogen and helium, so that's the 1s. There's 2 boxes until I run into the 2s. There's 2 boxes until I run into the 2p. There's 6 boxes until I run into the 3s, so 2p6, 3s. And there are 2 boxes until I run into the 3p, so 3s2, 3p. There's 6 boxes again, so p holds 6, until I run into the 4s. And for the 4s, I only need to describe potassium, so there's only 1 box right there, so 4s1. And I can add these up and see that's 10, 18, 19 electrons total. And all my subshells are holding the right amount. S is holding 2, P is holding 6. I can see that this is a ground state electron configuration, meaning I listed the subshells in order. I didn't make this 4s jump up into a 4p or something like that, which can happen, but that's an excited electron configuration, excited state. If I'm going to write an abbreviation, I can describe all of the electrons that exist in the noble gas that precedes the thing I'm talking about. So this right here is the electron configuration for argon, which has 18 electrons. So I could write all 18 electrons, or in the abbreviation I just write argon, put it in brackets, and you can only use a noble gas for that because you're talking about totally filled shells, totally filled S&P shells. Okay, and then after argon, I talk about the valence electrons. So I've got this 4s sticking out, 4s1. So this is 18 electrons that argon has, plus 1 more that potassium has, for a total of 19. So a few other things you need to know about electron configuration. You should be able to look at this and know, okay, there's a total of 4 shells. On the first shell, there's 2 electrons, right, for those guys right there. So we'll put 2 electrons. On that second shell, there's 2 plus 6 more, so there's 8 on that second shell. 1, 2, 3, 4, 5, 6, 7, 8. On the third shell, there's 8 again for the 3s2 and the 3p6. And then you can see on the fourth shell, there's just 1. So that way you could answer how many electrons are in each shell and in each subshell. Hope that helped.